This video is a supplement to my second lecture. I will prove the Ionin Pestov inequality and the first variation formula for length in this video. So first, let's deal with the Ionin Pestov inequality. I will follow the presentation in the textbook of Ionin and Barrera. So recall the statement. Given a domain omega, the curvature of its boundary satisfies the maximum curvature should be greater than or equal to the square root of pi over the area of omega. Moreover, the equality holds if and only if omega is a disk. The proof is a geometric one. We claim that the omega must enclose at least one oscillating circle. The picture looks like this. So let's see why the claim implies the theorem. Suppose omega has area pi, but the curvature is always less than 1. Then we know that the oscillating circle must be large and has area greater than pi. Then this contradicts the claim. Because the domain cannot enclose a large circle. Okay, so now we turn to the proof of the claim. We prove it by contradiction. Suppose all the oscillating circles exceed omega. So the picture looks like this. Okay. Now we shrink the oscillating circle radially until it is contained in omega. Okay. And the new one is called the in circle. And we call the Q the place where sigma is tangent to boundary omega, the contact points. Okay, note that there may be many contact points. And we know that every oscillating circle has to shrink a certain amount. Okay, this is by the compactness argument. The amount of shrink is greater than 0, and since gamma is compact, it must be greater than delta. So it leads to the fact that P and its contact points are far away. The distance between them is greater than some constant delta. Okay. So now let's start with the fixed point P1, and we reform its in circle and let the contact point be Q1. Okay. And there are two arcs from P1 to Q1. We choose an arbitrary one and name it gamma 1. And we split the in circle into two parts according to their relative position with gamma 1. So this sigma 1 in is closer to gamma 1, or in other words, gamma 1 out, sigma 1 out, and gamma 1 encloses sigma 1 in. And let P2 be the midpoint of gamma 1. And the crucial observation is that the in circle of sigma 2 of P2 cannot intersect sigma 1 out. Okay. So to see this, so we assume that if sigma 2 intersects sigma 1 out, then from the picture you can see that it must intersect sigma 1 in twice, okay, from the upper arc and the lower arc. And therefore, sigma 2 will intersect the in circle sigma 1 in at least 3 points. And this is impossible because two circles cannot intersect more than 3 points. And this is because 3 points determine uniquely a circle. Okay. And as a consequence, all the contact points of P2 must lie on gamma 1. Okay. So the Q2 must look like this. And from P2 to Q2, we call the arc gamma 2. And since P2 is the midpoint of gamma 1, we know that the length of gamma 2 is less than or equal to half of the length of gamma 1. Continuing this process, and we get nested arcs. Gamma 1 contain gamma 2, contain gamma 3, and each time the length is decreased by a half. Therefore, the limit of the length is 0. And so the intersection of all gamma I must be a point. Let me call it P infinity. The limit of contact points is also P infinity because each contact point Qi is the an endpoint of gamma I, and therefore, moreover, this Q infinity by continuity must be one of the contact point of P infinity. So this leads to a contradiction. And so we finish the proof of the claim and hence the Ionin-Pestov inequality. Oh, and I should make a remark that this claim or the Ionin-Pestov inequality has a poetic name. Looking at the picture, in Petronin and Barrera's book, the inequality is called a moon in the puddle. And you can see from the picture why it's the case. Now let's turn to the first variation formula of length. The argument I present is in lemma 3.2 of Ben Andrew and Paul Bryan's paper. So first, let's see the setup. We have a bounded domain omega in the plane, and we parameterize its boundary omega by x. So now we consider a family of a curve sigma. Okay? So this red one is the base curve, and we vary it. So the gray one is the variation. We assume that all these curves sigma have endpoints on boundary omega. So its endpoint is sigma 0 and sigma 1. They are given by x of some u plus s and u minus of s. Okay. S is the variation parameter. And we denote a variation field d sigma ds by eta n plus c t. Eta is the normal variation and c is the tangential variation. And the t and n are marked in the picture. And we denote by k the region in omega bounded by sigma. So we will assume that the variation preserve the enclosed area. Therefore, the area of k sub s should be constant along the variation. So we can compute the area by line integral, okay, using Green's theorem. So the area of k sub s are given by this. Okay. So here we abuse the notation. You look at the form of Green's theorem, x dy minus y dx. Therefore, if we plug in parametric equation, this is nothing but the normal component of the cross product of sigma and its derivative. Okay, so we have this formula. Note that k is bounded by the boundary of omega and sigma. So we have two integrals. Okay. So we differentiate in S, and we get for sigma, we get the variation field, and the derivative is the unit tangent times the speed sigma x. And when the derivative falls on the derivative, we get the second term sigma cross the derivative of the variation field. And for the derivative of the second integral, note that x is keep fixed during the variation. So by the fundamental theorem of calculus, we differentiate the upper and lower limit to get these two terms. And we know that the endpoint of sigma is on the boundary. Okay, so we have this relation, and the variation field, okay, is then has this relation with the tangent vector. Okay, if you want to keep your endpoints on the boundary, then the variation must tangent to the boundary. Okay, so we have this relation, and putting these together, we can simplify the derivative of area, and the end result is the integral of eta times the speed okay. So maybe let me say why we have this. Okay, so for the first term, n cross t. Okay, this actually is the only term that remains. T cross t is 0, and for the second term, we can integration by parts. So and we are left with another eta. So there's a 1/2 here. So at the end we have 1 eta, and the boundary term will cancel out the third and fourth term by the relation I just tell you. Okay. So at the end, the derivative of area is just the normal component of the variation. Next, we compute the derivative of length. Okay. We know that the length is the integral of speed, and therefore the derivative gives us t times the derivative of variation field. And when the derivative falls on eta, we get t dot n, which is 0. When the derivative falls on n, we get the curvature. Okay, this gives us the first term. And when the derivative falls on eta, we can integration by parts to get eta on the endpoint. When the derivative falls on t, we get t dot t prime, which is 0. Okay, so we are left with this relation. And here, this k sub sigma is the curvature of sigma. Okay, so let's compare the derivative of L with the derivative of A. Okay, you recall that the derivative of A is just eta itself. So now, if the area is kept fixed, then the integral of eta must be 0. And now we recall that this picture along the boundary. The variation field, it should be tangent to the down boundary. Okay, therefore, if either eta has non-constant curvature or does not intersect boundary omega orthogonally, if it does not intersect boundary omega orthogonally, then we can C will not be 0 because T is TT will then transfers to the tangent of boundary omega. Then we can construct a variation such that the length is strictly decreasing while the area is fixed. Okay, therefore, the critical point of this isoperimetric problem has to be of constant curvature, and it must intersect the boundary omega orthogonally. And on the other hand, we see that the derivative of length and the derivative of A are differed by an additional factor k times kk sub sigma. Therefore, we get these two conclusions that I present in the end of my second lecture. The critical points of the variation problem must be circular arcs intersecting boundary omega orthogonally. And if I have a family of perfect arcs, then the length taking derivative with respect to the area must be the curvature of the perfect arcs. Okay, so this ends my supplementary video.